Hello and welcome again to Flipped Harber for Calculus. In this video we're going to talk about continuity. Our objectives for this lesson are to learn how to express continuity using limits. The outline for this video, we'll take a look at what is an example of a continuous function. We'll take a look at what's called a whole discontinuity and then a jump discontinuity. We'll talk about asymptotes. We'll take a look at a definition of continuity, and then we'll take a look at some theorems about functions and where they're continuous, and then we'll end by talking about what's called the intermediate value theorem. Now here we see an example of a continuous function. Basically, the way to think about continuity is if you can put your pencil down and draw the function without picking your pencil up again, then it's continuous. To say that a function is continuous just simply means that every single point is defined. For every given x value that we're interested in, there is a y value, and it's right next to the points before it and the points after it. So let's take a look at a whole discontinuity. Very similar graph, but there is a hole at -5, and what that hole represents is a gap in the function where for a particular x value, -5, the function is not defined or is not defined right next to the points next to it. So this is what we refer to as a whole discontinuity. A jump discontinuity has the graph being broken. We see a nice continuous curve that ends at -5. There's a big jump to a totally different y value, and then the graph continues on again from -5. So this is a jump discontinuity rather than a whole discontinuity. Asymptotes are another example of discontinuities. Now, whatever this function is, it looks like it goes up together, but there's an actual gap at that vertical asymptote. This vertical asymptote happens to be x equals 0, and this is another example of a discontinuity because the graph is broken. It doesn't actually go from negative to the positive x values with a continuous curve. So you actually have to pick your pencil up, go over that asymptote, and then continue your graph. So let's take a look at an actual formal definition of continuity. A function is continuous at a. Now a is an x value. Okay, think of it as a function is continuous at 5 if the limit as x approaches that a value equals f of a. That means that we don't have some gap in our function. It means that as we approach that number from the left and from the right, it actually equals what the function should equal. Now, let's take a look at some theorems. If f and g are continuous at a, that means that f is a function, g is a function, and they are continuous at some x value we're interested in. Then functions that are made from them are usually always continuous. And here's an example of ones that are always continuous. If we add the two functions, that new function is continuous. If we subtract the two functions, that new one is continuous at the x values that we're interested in. And c of f means if we multiply by some constant, maybe if we multiply the whole function by 10, that new function is still continuous at a. If we multiply the two functions, still continuous. If we divide the two functions, it's continuous as long as g of a does not equal 0. Separately, it's okay if g of a equals 0, but as soon as we put it in the bottom of a fraction, we can't have that. That new function would be discontinuous if g of a did equal 0. So we have a theorem that says Polynomials are like the most basic functions that we deal with. They are always continuous. no matter how complicated your polynomial is, no matter how high that order is on a polynomial, if it's just a polynomial, you know, x to the fourth, x cubed, x squared, stuff like that, it's going to be continuous everywhere. So from negative infinity, we've got a negative missing right here. Let's put it in there. So from negative infinity to positive infinity, polynomials are always continuous. You can draw them, they go up, they go down, they cross the x-axis all over the place. They're continuous. Rational functions are also continuous everywhere it's defined. It is continuous over its domain. We'll take a look at what this means in a second. So first of all, let's go ahead and take a look at a polynomial function. We've got this cool, looks like it's probably an x to the fourth polynomial. Could be something different, but I'm seeing 4 roots, so I'm guessing it's an x to the fourth function. This is continuous everywhere. It continues on up and to the left forever. It continues on up and to the right forever. This function is continuous everywhere. We could draw it forever without ever picking up our pencil. If we take a look at a rational function, and I actually gave you the rational function here, it is continuous everywhere that the bottom doesn't equal 0. So it's going to be discontinuous at 1 and at 4, but everywhere else it's going to be continuous. So here's another theorem. Basically, it's a list of continuous functions. Now, again, when we say that they are continuous in their domain, what we mean is as long as this function isn't blowing up, as long as we don't have 0 on the bottom of the fraction, as long as we're not trying to take an even root of a negative number, things like that, these are continuous functions. So if it's got points where it blows up, what we do is we create regions of continuity. We can say that it's continuous from 2 to 4, or we can say that it's continuous from negative infinity to 1. So we create regions of continuity where it's defined. So polynomials, they're continuous everywhere, always. They're great to work with because they're always continuous. Rational functions, they're going to be continuous wherever the bottom does not equal 0. Root functions, basically if you can take the square root of it, it's going to be continuous. Obviously we're not plugging in negative values into that square root. We can plug negative values into that cube root. Any odd root we can plug negative values in. If it's an even root we can't plug values in, it's not going to be continuous there. It's actually not going to exist there. But everywhere else they are continuous. Trig functions, sine and cosine, they're continuous everywhere. They just kind of go back and forth waving all the way along. Tangent, it's got regions of continuity. Where the tangent is undefined, we just don't talk about it. But in between those spots where it's undefined, then it's continuous. Inverse trig functions, they're continuous. Exponential functions, well, exponential functions are defined everywhere. We can plug in negative values into those, we can plug positive values into those, we can plug zeros. Exponential functions are continuous. Logarithmic functions, can't plug a negative in there, but where we can plug in numbers, it's continuous. No holes, no jump discontinuities, they just move on nice and smooth. Now, when we talk about composite functions, you know, f of g or g of f, where we're taking one function and plugging it into another. We have a theorem that says if f is continuous at b, okay, so at some x value, 6, and the limit of another function equals that number, then we can take the limit of the composite function f of g, and it's just equal to f of b. Really what this does for us is if we're taking the limit that is defined, and we need to, we can move that limit inside if we want to. Another theorem about composite functions is just the simple fact that if g is continuous and f is continuous, then their composite function is continuous. All right, really all of this brings us up to the intermediate value theorem. Intermediate value theorem. It sounds a little bit complicated until you really stop and think about what it means. So I'll give you a second to write the intermediate value theorem down. Pause the video, write it down, and then start the video back up and I'll start talking about it. So the intermediate value theorem basically says that if we have a continuous function from A to B, now those are x values, if we have a continuous function from A to B, and notice that that is inclusive. We have these square brackets around A and B. That means that we're going to include A and B. And let n be any number strictly between f of A. So I'm going to have my f of A be right here. And I'm going to have my f of B be right there. Now these are just y values. Means that when I plug in A, this is the number I get out. When I plug in B, this is the number I get out. If n is between f of A and f of B, well, if I have to get from here to here in a continuous fashion, because it's a continuous function, so no matter how I get there, at some point I have to pass through n, that's a y value, and I have to pass through it between A and B. So there has to be some c value where f of c equals n. All the intermediate value theorem says is if I start at this y value and I have to get smoothly up to this y value, then I have to include everything in between it. So it sounds complicated, but it's really not. Okay, so that's the end of the lesson. Time for you to get to work. Try some of these on your own. I'll see you in class, and I'll see you online.